Hello everyone, my name is Zineb Idrisi. I am PhD student in 5th year at NSEM. My article is titled Optimal Coordination of Directional Overcurrent Relays Using Genetic Algorithms with DG Penetration Distribution Networks. The plan of this presentation is as follows. We start with an introduction, then we will present the problem formulation, then we will give the setups of the genetic algorithm used in this work. After that, we will discuss the results of the simulation obtained. Finally, we will conclude and give perspectives. There are many reasons why the integration of distributed generators directly connected to distribution networks has become a potential solution worldwide, which are Regulation in Force Law 1309, the increase in demand for electrical energy, high cost of building large generation plants, and ecological constraints and advantages, climatic factors, and new technologies for small productions. But this connection has also negative effects on the performance of the distribution network in terms of electrical energy, voltage plane, transit direction, and fault current. This change to network can lead to protection coordination problems. The problem of coordination of directional overcurrent relays is considered as an optimization problem. Its objective function is the minimization of the sum of the operating time of all primary and backup relays in all fault locations studied, taking into account the constraints of selectivity, sensitivity, reliability, and characteristic of relays. The most important constraint is the coordination constraint. Coordination time interval (CTI) must be imposed between a primary and backup relay pair to maintain coordination. The value of CTI varies between 0.2 and 0.5 seconds, usually taken as 0.3 seconds. The difference in operating time of backup relays and primary relay must be greater than CTI for all pairs of relays. CTI depends on some factors such as circuit breakers opening time, relay overtravel, tolerance, and relay setting errors, as shown in the following table. Moving now to the characteristic of the relays, the operating time of directional overcurrent relays is expressed as follows, with TDS is the time dial setting, IF is the primary fault current at the current transformer terminal, IP is the pickup current, E and B represent the constants for the relay characteristic, as mentioned in this table. The relay should not take long to operate, and it also needs a minimum of time to do so. In our case, the minimum operating time is equal 0.1 seconds, and the maximum operating time is equal 4 seconds of each relay. The limits of TDS usually specified between 0.1 and 1 seconds, and the limits of PS are calculated using following formulas. The minimum values is the large between the minimum available tap and the product of the maximum load current. The maximum values is the smaller value between the current corresponding to the maximum available tap and 2/3 of minimum fault current. To solve this problem, we use the genetic algorithm since it can find the global optimal solution of any optimization problem. The operating time of relay I is expressed in the following equation, where x represents the vector of variables. The value of the parameters of genetic algorithm for the studied system are given in this table. The following chart summarizes the various setups of the genetic algorithm. In order to study the behavior of protection relay coordination in the studied system in the presence of the distributed generators, two scenarios are proposed. The first one consists in determining the optimal values of the parameters of 24 relays existing in the distribution network interconnected 9 buses using genetic algorithm. The second one is the use of the genetic algorithm on the network containing the 4 generators to find new parameters and solve the coordination problem. The genetic algorithm is applied on 9-bus interconnected distribution system to obtain the optimal parameters of relays, which are PS and TDS. The relays R17, R19, R21, and R23 are assigned without backup. The characteristic constants of relays are normal inverse. The simulation results are shown in this table, and the evaluation of the objective function are presented in the following figure. The objective function is the total operation time of relay in this system, which is 51,722 seconds, and the convergence time is 47,548 seconds. The operation time of primary and that of backup relays, as well as the coordination time interval between 32 pairs of primary backup relays, are given in this table. As it is shown in the results, CTI is greater than 0.3 seconds for each primary backup pair, as well as the sensitivity and reliability constraints are also well respected. With the addition of distributed generators to the distribution system, the short-circuit current values has increased. In addition, new combinations between the primary backup relay pair are selected in the presence of DGs. So there will be 44 pairs of primary backup relays. The result of calculation of operating times of primary and backup relays that are performed with the same TDS and PS font in the first scenario, and the calculated CTI of all pairs primary backup relays are given in this table. It can be seen that 19 coordination violations appear in this table, which are shown in bold. The CTI of some primary backup relays are less than 0.3 seconds. It can be concluded that the coordination of the relays can be reestablished when the setting of these relays is readjusted with a new setting different from the original one before the connection of the distributed generators to the distribution network. It is in this context that a second scenario must be implemented. The new optimal TDS and PS setting are presented in this table. The evaluation of the objective function using genetic algorithm in the presence of distributed generators is shown in the following figure. The values of the objective function is 94.75 seconds, and the calculation time of genetic algorithm is 77.42 seconds. The results of the calculation of primary and backup relay operating times with new TDS and PS setting and the calculated CTI of all primary backup relay pairs are given in this table. It's clear that the CTI is greater than 0.3 seconds for all pairs of primary backup relays. We can deduce that the application of genetic algorithm on this distribution network can solve the coordination problem in the presence of distributed generators while respecting all constraints. With the installation of distributed generators in this network, the short-circuit current values are modified. Because of this change, relay coordination was lost between 19 pairs of primary backup relays. To restore relay coordination, the genetic algorithm was implemented on distribution network in the presence of distributed generators. The simulation results show that this algorithm provided an efficient and robust high-quality solution. Research of adequate solutions to limit these impacts is considered as a perspective. Thank you for your attention.